we were on quick review. Quick review before we go back to example 3.3 it was, right? 3.3a, 3.3b. That's what I have on my notes anyway. So the visible spectrum, what we said is the light we see is a certain portion of the entire electromagnetic spectrum, and that this electromagnetic energy, as depicted here, goes from a longer wavelength. So larger wavelength, capitalized, bold, larger wavelength, has a correspondingly small frequency. It doesn't make as many oscillations per second. Long wavelength, small frequency. On this end, small frequency, therefore long wavelength. No, high frequency, and a low, not long, a short. So a larger frequency, smaller wavelength. Smaller frequency, larger wavelength. Those things are inversely proportional. But we also said that frequency and energy are directly proportional. So when the frequency is low, the energy is low. When the frequency is high, the energy is high. Which means when the wavelength is big, the energy is small. And when the wavelength is small, the energy is big. Those basic relationships are what you need to keep straight. Energy directly related to frequency, which is inversely related to wavelength. Okay, and then the Roy G. Biv goes from a smaller wavelength, a longer wavelength, smaller frequency, to blue, or violet, actually at the other end, is a smaller wavelength and a higher frequency. Right, so he said, well, remember that by going wavelength. We're talking wavelength. Roy G. Biv. Roy is big, violet is small. Roy G. Biv is the wavelength. And whenever we need to determine the color of light, the chart we have is based upon wavelength. So if we needed to figure out the color, we would go figure out the wavelength, look on page 100 for the chart, and then figure out what color it would be based upon the wavelength. In nanometers, which is times 10 to the negative 9th meters. Okay, so we were doing 3.3a. Actually, I think we did 3.3a. Let's go through it one more time. Example 3.3a. The light is given that has a frequency of 2.3 times 10 to the 16 hertz. What is the energy? And so we have this basic formula we're going to use all the time. This is one of the two formulas for the whole module, right? The first one is that you could memorize it either way. Speed of light is equal to wavelength times frequency, or frequency equals speed of light divided by wavelength, or wavelength equals speed of light divided by frequency. They're all different ways of saying the same thing. And this second formula for energy. Energy is equal to Planck's constant times the frequency of the wave. Planck's constant is just that. It's a constant, and it'll be given to you. So 6.63 times 10 to the negative 34th joules per hertz, or joule seconds is the way it's said, but joules per hertz is a joule second. So this part of the math will always be given to you, and this second part is whatever the frequency of the wave you're considering is. In this case, the math works out to be 1.5 times 10 to the negative 17th joules, and you can see that answer on page 107. Now they note in there that the answer is only to two significant figures. Why would it only be to two sig figs? Go ahead.
That's how much the significant, or that's how much the scientific notation shows.
Well, it shows 3 here and 2 here, right? And the answer needs to have the same sig figs as the least. So the least is 2, therefore the answer can only have 2. Now I told you before, when we convert times 10, the meters, that sometimes when I put it in nanometers, I add the 0, and it's technically not, it still should be in scientific notation, but your chart is not in scientific notation. So that's one of those things where if you had 6.4 times 10 to the second nanometers, and you wrote down 640 nanometers, it's the same, I know that 640 is what you'd actually look at on the chart. The second part, I don't think we got to this one, because this could be done either as a 1-step or a 2-step solution. It says the light wave has a wavelength of 1.21 times 10 to the negative 12 meters. What is its energy? So again, going back to the same formula, that energy is going to be equal to Planck's constant times the frequency. But we don't have the frequency. We have the wavelength. So we have to use the first formula to convert from frequency to wavelength, use the second formula to convert from from wavelength to frequency, and use the second formula to convert from frequency to energy. You see that? Okay. So given wavelength, we use the first formula in the book that we're given. We're going to convert that wavelength into a frequency, take that frequency and plug it back into our formula for energy to compute the answer of what is the energy of that wave. So the frequency is equal to the speed of light, 3.0 times 10 to the 8th meters per second, divided by the wavelength. Here's our formula. We're doing it here. Speed of light divided by the wavelength. And again, just so we get used to this, what should my answer be about, approximately? Let's approximate the answer real quickly. Look at the coefficients of the scientific notation. Do you all see that we're looking at 3 divided by 1.2? 1.21. Okay. What is 3 divided by 1.2 about? About 2.5, right? 1.2 times 2 would be 2.4. 0.6 would be half of that, 2.5. So we're looking at 2.5 times whatever the scientific notation works out to be. 2.5 times 10 to the what? We've got an 8 divided by a negative 12. Now when we divide, we subtract the exponent, right? So we've got 8 minus a negative 12. 8 minus a negative 12 is positive 20. Because subtracting a negative is the same as adding a positive, right? And that should be from Algebra 1, okay? So 2.5 times 10 to the 8th plus 12, or 8 to the 20th. And that's what actually the answer is, exactly 2.5 times 10 to the 20th hertz. Okay. Are we done?
No, definitely not.
Because we were asked for energy, right? So energy is equal to Planck's constant times the frequency, which we just solved for. Planck's constant is given, always the same, 6.63 times 10 to the negative 34th joule seconds, and the frequency of 2.5 times 10 to the 20th hertz. Now again, let's estimate that. What would my estimation be? First, the coefficients. 6.63 divided by 2.5. Well, 2 times 2.5 is 5, and I need another 1.5. So I know it's a little bit more than, but let's just say it's half of 2.5, so it's like 1 1.25, right? So 2 would be 5, divided by this would be 1, 2. 2 would be 5. So again, we're looking at about 2.5, right? Is that about right? 2.5 times 2.5 would be actually more than that.
3.2.
Okay, you say 3. 3 times 2.5 would be 7.5, so that's too big. It's got to be less than 3. 2, it's somewhere between 2.5 and 3. We good with that? Okay, so if you look at that and say it's 6.63 divided by 2.5 is somewhere between 2.5 and 3. And times 10 to the what? What is going to be the exponent of my answer? How would I find it? Between 2.5 and 3 times 10 to the okay, take the exponent of my numerator, which is negative 34, and I take the numerator of my denominator, or excuse me, this is straight multiplication, right? So what do we do with the exponents? We add them. So can anybody in here, juniors in high school, tell me what negative 34 plus 20 is?
Negative 14?
Negative 14.
Oh, negative 13.
Well, 14, 6 times, see, because we did division, that's what was the problem. See, because it was 6.5 times 2.5, not divided by 2.5. That was my bust. See, 6.5, about 6.5 times 2.5, that would be 13 plus another half, 14, 15, 16 and a half to 17. 17 times 10 to the negative 14th, which is 1.7 times 10 to the negative 13th. That was my bust. So our approximation should have been this times 10 to the negative 34th plus 20. So 17-ish times 10 to the negative 14 is written as 1.7 times 10 to the negative 13. Okay? Now, question is that the only way we could have done that problem? No, we could use a one-step method. The one-step method would have been, okay, I've got wavelength. I need to solve for energy. To solve for energy, I need frequency. Here's the formula for frequency. I can take my formula and plug in what frequency would be. Frequency would be the speed of light divided by the wavelength. I plug that right into the formula so that my math is now Planck's constant times quantity, speed of light divided by wavelength, which is a way of writing frequency, right? And I have every one of those components. I have h, c, and lambda. So I just plug them into it directly. So rather than solving for frequency and then plugging it in and solving for energy, I can put in the variables for frequency and solve it directly for energy. And the answer, of course, turns out to be the same. For you, if it's easier for you to think, okay, I'm going to solve for frequency, and then I'm going to solve for energy, that's fine. If you were to go and do it as a one-step method and plug in the variables that represent frequency and then solve it in one step, awesome. That's fine too. Ultimately, for example, 3.3, it's 1.7 times 10 to the negative 13th joules. Now, because I was called out, because it's time, let's do 3.6 and maybe 3.7 together. And then I'm going to talk about homework, and we'll maybe spend the last few minutes making sure we understand the assignment and any questions you might have on those problems. So again, normally you would do this completely on your own. Let me drive through this so we have some time to talk about some homework. On your own, 3.6 says, if a light wave has energy of 3.4 times 10 to the negative 14th joules, what is its frequency? Okay. So an energy given a frequency of what? So, do you see that we're kind of working the problem backwards now? Rather than driving towards energy, now we're taking energy and driving back towards either frequency or wavelength. So we still are going to have the same formulas, right? Energy is still equal to hf, Planck's constant times the frequency. But now I need to solve for frequency. That's what we've been asked for. So I look at my formula, and I have to rearrange that to solve for frequency. What does that look like, rearranged algebraically, so that I have an equation that says frequency equals something? What does it look like? Again, this should be 9th grade Algebra 1 stuff, so just so you can feel confident in yourself. Yes, ma'am?
Well, you divide the h on both sides.
Okay. You take this, you've got h times f, you're trying to solve for f, so you get rid of the h by dividing both sides by h, and it rearranges to look like that. Frequency is equal to energy divided by Planck's constant. Another shortcut way of thinking about it is, you know what? This is pure multiplication, and so these are both over 1, and I can solve by sliding pieces across the diagonal. Here, it's e over 1. I'm trying to get rid of the h. Let me slide it down below. E over h. Okay? So the frequency is equal to the energy of the wave divided by Planck's constant. Do I have everything I need to solve it? Yeah. I've got the energy and Planck's constant. It will be given to us. There's the math. So I've got 3.4 divided by 6.63. Let's do a quick estimation now. It is division this time, right? So you see it's 3.4 divided by 6.63. What do you think that is about? Well, look at it and go, it's slightly less than 2, right? Because 2 would be 6.8 divided by 6.63. So it's a little bit less, or it's less than 2. Well, in my mind, okay. We got 3.4 divided by 6.63. If it was 6.8, it would be half. It would be almost 1, so it's about half of that, right? Again, different minds work different ways. 3.4 divided by 6.63. It's less than a half, but not much less than a half, right? But in our mind, let's say maybe just say 0.4. Does that sound reasonable? 0.4? Make sure I did it the right way, because I'm infinitely fallible as well. A little bit less than 0.5, so we'll say 0.4 times 10 to the what? And more specifically, what's the process? How I'm going to figure out what that exponent's going to be? what is times 10 to the 14th divided by times 10 to the 34th? What am I going to do, people? What's the math I have to do? Subtract them. So I'm going to take negative 14th minus a negative 34th. Subtracting a negative is the same as adding a positive. So negative 14 plus 34 equals
20.
positive 20. Good. It's like pulling teeth, and I've got a couple of bad ones, so if I could choose the tooth, that'd be fine, but okay. So we've got a little bit, we got about 0.4 times 10 to the 20th, which in scientific notation would be 4 times 10 to the 19th, right? Is that what we get? Survey says, okay. So it says 5.1, which would say that we're a little bit more than a half, which makes sense because if we were at 3.3, it would be a half, right? I let you think with me the wrong way. But we knew it was about half, but in this case, a little more than half, not a little less than half. 5.1, okay. If I had assumed it was 4.9 and I got 5.1, I'd look at it and go, oh, I see what I did. I said this is a little bit less than half. It's actually a little bit more than half. That was my fault. But the exponent is exactly on. So if I'm off by a tenth, realize it's times 10 to the 19th, which means I'm really off by a lot. But I would check my calculator again and go, it's probably right. My calculator, I must have made a little mental error. But frequency is 5.1 times 10 to the 19th hertz. Any questions on this process? So we're just taking energy going backwards. And then 3.7 says I've got an energy of 3.3 times 10 to the negative 19th joules. What's the color? If you're asked what the color is going to be, what are you ultimately driving for? Wavelength, right? The only method you have right now to convert from something to color is through wavelength. So we're going to drive back to wavelength. What did we just drive backwards to? On the last problem, we drove backwards to frequency, right? So if we do the same thing, we're going to drive back to frequency and then use the other formula to convert from frequency to wavelength, which is what we do. We've got these two formulas, and you can do it as a two-step process or a one-step process, driving backwards from energy to get frequency and then using frequency to get wavelength, or combine them together. So we have to rearrange, since we're solving for frequency, into that form and plug in the numbers. So our energy is 3.3 times 10 to the negative 19th joules divided by Planck's constant, and that gives us 5 times 10 to the 14th hertz. That's our frequency. This waveform is oscillating 5.0 times 10 to the 14th times per second. How much energy is that? We take the second formula, the first formula we learned, the second one on the board, frequency is equal to the speed of light divided by the wavelength. Just plug it in and solve it. So there's our frequency, there's our formula. We rearranged it to solve for wavelength. Speed of light divided by the frequency, which we just figured out using the energy working backwards to frequency. Plug that in, and we get a wavelength of 6 times 10 to the negative 7th meters. Oh, we're looking for color. Color's in nanometers. So what is that in nanometers? Right, now written in scientific notation, that many nanometers. Do you see that the nano right there could be written times 10 to the negative 9th? And then 2 plus a negative 9 gives me a negative 7. Right? Everybody, did everybody first hear that? Okay, does everybody understand that? Not so much on the second part. Let me say it again. We know that nano, right there, that n in nanometers could be written as times 10 to the negative 9th. Right? If I were to take this, the negative 7, and I need it to be times 10 to the negative 9th, to still have the value of negative 7, I would have to have a positive 2 to add to it. Think of it that way. The sum of negative 9 plus 2 is the -7. If you need to, you could take 6.0 times 10 to the -7th meters times conversion factor of 1 nanometer divided by 1 times 10 to the -9th meters. Now that should sound familiar from Module 1, right? Conversion factor from meters times 1 over nanometers times 10 to the -9th meters, 1 nanometer over 10 times 10 to the 1 times 10 to the -9th meters. Do that math to get nanometers. You would have 10 to the -7th divided by 10 to the -9th. Times divided by times 10 to the -9th would be -7 plus 9, which gives me 2. So either way. But ultimately, we've got to put this in the form of nanometers. And when I go look at the chart, what number am I going to look for? 600, right? There are 600 nanometers. When we do that and look at the chart, this is a yellow light. Okay, so this wave that had that energy, because of that energy, has this frequency, and because of that frequency, it appears to our eye to be that color. So we're either working from frequency or wavelength to energy, using both formulas, or working from energy backwards to go back to frequency or wavelength. We can go to frequency directly, we can go to wavelength as a two-step. We go forward, we can go from frequency to energy directly, or we can go from wavelength to energy as a two-step.